Hi, my name is Jennifer Huang.
And I'm Kelvin Liu.
Today we're going to introduce our final project for machine learning, Mandarin tone learning.
Mandarin tone learning is a tool that aims to help people learning Mandarin Chinese. As the name implies, we focus on Mandarin tones. In Mandarin, each character has a tone, and there are a total of 4 tones, as seen in the picture. These 4 words are pronounced as follows.
Ah, 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 ah.
都很难东西所以如果你不相信你的生命，放弃很容易大部分创始人放弃但是最好的创始人不放弃，所以相信你的生命和不放弃非常重要。
In the video, Mark Zuckerberg demonstrates his fluent Mandarin. However, his tone pronunciation is quite poor. This is part of the motivation behind this project.
First and foremost, tones are often the most difficult aspect of learning Mandarin. Additionally, incorrect pronunciation of tones leads to miscommunication with native speakers, and sometimes even discouragement on the part of the learner. Before going into the technical details of the project, here is a very quick demonstration. So the user is presented with a very clean and simple interface. They are prompted to say this word, and to begin recording, they only need to press space. 就. When they press space once again, the program stops recording and predicts the tone that they used.
The program also detects incorrect pronunciations. This character is bao, its first tone.
However, when I pronounce it with the 4th tone, the program intelligently figures out. Bao. This project uses supervised learning to classify the tone of a user's recording. We consider 4 classes, one for each of the tones.
The algorithm we chose to do the classification is supervector machines, mainly because many related research papers utilize this method with great success.
Our dataset comes from Yo-Yo Chinese, which has a table of all the possible pinyin combinations. For each pinyin character, Yo-Yo Chinese has all 4 tones.
北北北北科可可克
We collected roughly 1,600 recordings from Yo-Yo Chinese, and it's important to note that each recording is very clean with little background noise, and there is high emphasis on the tone pronunciation. In order to simulate how different types of people would use this program, we collected about 100 recordings from real people. These recordings had some background noise and featured more authentic pronunciations. In order to transform each sound recording into a format that we could use to extract features, we first had to do some audio signal processing. We did this using Pratt, a program used by many linguistic analysts.
Here is an example of just one recording. The recording is transformed into a pitch contour, which is a plot of pitch versus time. This contour takes the pitch of the recording in 1 millisecond intervals, and the resulting data can be saved as a text file. We wrote a script to automate this process for the entirety of our dataset. We adapt the feature extraction algorithm from a Chinese research group. In order to normalize, each value in a recording's pitch contour is first divided by the mean pitch. The pitch contour from each recording is split into n segments, and we use linear least gauge to find a line to fit each segment.
When we construct the feature vectors, each segment contributes 2 features. First, the slope of the linear least squares line of that segment, and second, the average value of the segment. In our project, we found that n equals 5 yields the best results, and thus each of our feature vectors were of length 10.
Out of the 1,600 recordings from Yo-Yo Chinese, we used 1,300 as a training set and 300 as a test set. After tenfold cross-validation, the error of our model on the training set was 1%. Furthermore, the error on the test set was 1 to 6%.
On the most basic level, these results imply that machine learning can be used to predict the tone of a recording. Additionally, it implies that the feature extraction algorithm we employ provides us with features that are a good representation of the recordings themselves. However, when we introduced pronunciations from different people, the test error went up to 23%. This suggests that a training set based on only one speaker does not give ideal results. Furthermore, the tone that was most frequently misclassified was tone 3. This may be due to the fact that people pronounce the third tone differently in different contexts. The change in pitch is not always as emphasized as it usually is.
We began the machine learning side of this project in R using the E1071 package. Later, we migrated to Python and scikit-learn because we decided to create the final program in Python. While both the R and scikit-learn implementations of SVM are based on libsvm, the results between R and scikit-learn are not always the same.
Pygame was used to create the graphical user interface. Pygame also controls the logic of the program when a user presses a certain key. PyAudio was used to record the user on the fly. The quality of the recordings are not always great, however. Sometimes this causes misclassification by the program. The user interface of Pratt was shown earlier in the video. Again, we used this program to extract pitch contours from each of the recordings. Additionally, a library called Python Pratt scripts allowed us to execute Pratt scripts from within Python. After a user finishes a recording, the same Pratt script is run to get the pitch contour from the new recording.
In the future, we could change our dataset to include a wider variety of people. This would likely increase the robustness of our classifier. Also, many words in Chinese are not just a single character. Therefore, the educational aspect of our project could be expanded if we were to support multi-character words and phrases.
Finally, a user really only needs a microphone to use this program, so it would be possible to create web and mobile versions. This would allow users to improve their Mandarin pronunciation wherever they go.
Thanks for watching.